think we can probably start now. I know others will probably continue to trickle in. My name is Fernando Miralles Vedam. I'll be serving as host of this session. I'm with the Nature Conservancy. Welcome you. If you're here, you should be here for the session entitled Experiences with Remote Sensing Applications for SDGs and Water. So I hope that's what you are here for. But if not, we also welcome you. Just before we start, just some housekeeping items. The way we'll conduct the Q&A and the interacting with the audience in the session is through the Pathable platform. So the Zoom chat for the session is disabled. The reason for that is, it doesn't get recorded on Zoom. It gets recorded on Pathable, and we want to keep a record of the exchanges. So any questions you want to ask, we will be monitoring them, and the speakers can respond to them on the Pathable platform. There's a chat feature right underneath where you click to join. And there is a message there already from me welcoming everybody, so you should see that. The other housekeeping item, very simple etiquette. If you're not talking, let's just disable the microphone so that we have a noise control in the session. So we're excited to be here, and I'm very pleased to be accompanied today by a great group of speakers and myself. So I'm going to say a great group of speakers and me. So the great group of speakers will talk before me. And the objective of this session is to go through how remote sensing is enabling the exploration of sustainable development goals around water, right? So we have three presentations. The first one by my colleague Sujay Kumar at NASA, who will be talking about their Earth Information System platform and applied to fresh water and the different applications that they have enabled. I've been in recent contact with the EIS, the Earth Information System Group, and they're really doing remarkable things. And I think they'll be a delight to learn. That will be followed by my colleague Ivan Lalovic from JIBE, who will be sharing some recent experiences and how they're using remote sensing to tackle water quality in water bodies and some of the applications of that. And then that will be followed by a presentation by the Inter-American Development Bank. Unfortunately, our speaker, Ji-Hoon Lee from IDB, was unable to join. So I'm going to be making that presentation on the impacts of COVID-19 on water quality in Latin America, as measured by remote sensing. So those are the three sessions. And then we'll have a short Q&A session. But given that we're going to be interacting mostly through the Pathable platform, you can feel free to drop comments or questions anytime in the chat, and the speakers, myself and Ivan and Sujay, will be monitoring that in case we can, so we can respond. So we have a little bit of flexibility in how we exchange, and then we'll close it up. We need to be done in now a little bit of less than an hour and 15 minutes. So we got plenty of time in our hands, but also plenty to cover. So with that said, again, I welcome everyone to the session, and I'm going to turn it over to my colleague Sujay Kumar for the first presentation. Sujay, the floor is yours.
Thanks, Fernando. Good morning from where I am. I'm going to turn my video off because I'm not sure about my internet stability. So let me make this full screen. Hopefully that's coming through.
It is coming through.
Yeah. So like Fernando said, I'm going to talk about a relatively new effort called Earth Information System at NASA. I'm a scientist in the Hydrological Sciences Lab at NASA's Goddard Space Flight Center. So as many of you are aware, NASA has a ton of capabilities in remote sensing and modeling, and there has been a bit of an acknowledgement that some of these capabilities are a bit fragmented. While most of the scientists and practitioners of the data know where to go, to get these data sets, but it's not super obvious for perhaps societal applications and those type of things. So EIS is an attempt to put our arms around this. So our overall larger level goals are to really provide a comprehensive and open science platform, and I emphasize the open science aspect. And by integrating NASA's modeling and remote sensing and data assimilation and analytics and visualization to make the science more accessible and reachable to a larger audience. So using such a setup, we want to tackle complex and grand challenge problems in freshwater quantification, such as how is the water cycle changing and how are the frequencies and occurrences of extremes changing and so on. So we also want to acknowledge that the freshwater is not an isolated system. It is intimately connected to other Earth system components. So we want to establish those linkages with other Earth system components. And third, NASA has traditionally focused more on water availability quantifications because we have a ton of remote sensing platforms that can measure different aspects of water cycle, but not so much on the water quality side. So I'm really looking forward to seeing the other two talks today on that. And we have also made an attempt within the EIS to combine or connect water quality quantifications along with water availability quantification. And the final one is what I said earlier, to really extend and build on the open science paradigm to translate the NASA science, not just to scientists and practitioners of the data, they sort of know how to work with this, but also to a much larger audience, including non-scientists. So I'll describe some examples of all these efforts and in my slides. So there are 5 thematic areas, focus areas that we have defined for the current phase of the project. The first one discusses or examines connection between fire and hydrology, both pre-fire and post-fire. And similarly, the second task focuses on examining the risks to coastal areas from hydrological changes and sea level rise. And the third one focuses on encompassing the water security theme by simultaneously examining both water availability and water quality assessments. And then the fourth one examines the longer term impacts on water cycle fluxes and stocks, and how is the water cycle changing? What does the observational record tells us about these changes, and what type of non-stationarities exist, and how they affect the extremes and future projection. And finally, the fourth one, a bit of a technological focus, where we use AI-based methods to develop a unique science translation capability and show an example of that. So I'll focus a bit more on each of these specific areas. The first one is focusing on examining the linkages between fire and hydrology. So before I get into that, I also want to say that in this phase, we've truly embraced the theme of co-development. So in other words, we have been reaching out to a ton of people. That's how we came across Fernando and the Nature Conservancy. So while we are building these case studies and studying these problems, we want to orient our science specifically towards the societal development goals, so that the science, when developed, is more obvious to people who are this is relevant for. So for the fire themes, and I'm going to list all the co-developers on each of these slides. So here we have been working with the U.S. Forest Service, FEMA, U.S. Department of Agriculture, and there's another domain that we are focused on in Amazon, and we have been working with researchers in the Amazon as well. So here, this is just an example just over the Western US. The domain that we are working with here is shown. And here, the synthesis is a large number of remote sensing data sets, which are also listed on the left here, including precipitation data from GPM, MODIS-based products, Landsat reanalysis, and so on. And the objective here is to show how the hydrological causes and impacts of fires have changed in the satellite era, and what do the satellite record tells us. So we are using a data product called OpenET, which is also a NASA initiative, where evapotranspiration estimates are from remote sensing are available. So this is just a quick example of what we can do, quantify based on remote sensing data set. And of course, in fire-based locations, gauge-based data sets are not routinely available. So that's where remote sensing becomes quite powerful. So the OpenET map, which is shown in this fractional ET or DisLXE, which is one of the OpenET models, that shows how the fractional ET, which is the ET post-fire compared to the annual average, compares. And those patterns are very well matched with the Landsat-based MODIS MTBS burnt area maps. And when you look at the time series on the top, you can see the blue line, which is the evapotranspiration over the, the red line that shows the evapotranspiration over the burned areas, and compared to the blue line, which is again evapotranspiration over adjacent areas not affected by fire. So you can really see after the fire, which is shown in the red bar, how the ET is suppressed over the forest location in this case, and it takes more than an year plus to recover. And we have done similar quantifications over other regions, savannas and grasslands, and they all show different recovery characteristics. So one of the neat quantification here is that because of the fire, there is a big change to the hydrological partitioning regime. So you have less ET and more runoff in those areas, and you must have seen in news reports in many places after the fire there is a mudslide or sort of debris flow sort of impacts and flooding that happens. So based on remote sensing, we can quantify what that overland contribution to runoff is. So in this, based on OpenET, we quantified that about a total volume of 330,000 acre feet is diverted more towards flows. So in other words, the risk of flooding increases significantly, and we can really quantify that from these remote sensing data sets. So we have similar quantifications over the Amazon, but I'm not going to discuss them today. So shifting to the second area, which is where we started looking at the coastal impacts and sea level rise-based threat to areas in the Ganges-Brahmaputra Delta, using Bangladesh as a case study. So, and that's uncovered some alarming water shortage issues, which are sort of typical of many river basins in the world. So Bangladesh is a developing country, and the needs of this growing population has driven a significant increase in the rice production in Bangladesh. And this is a report from FAO that shows the tons per hectare of rice production from Bangladesh compared to other major rice producing countries like India, Indonesia, Japan, and so on. So this increase in rice productivity is observed in our satellite records. So on the left, if you can see my mouse, it shows the LAI trend, leaf area index trend from NASA's MODIS instrument. And that shows an increasing trend in the last couple of decades. The satellites have also observed a decreasing trend in precipitation, likely driven by climate change and those type of impacts. So there is a reduction in amount of water available, but the agricultural production has increased at the same time. And as many of you know, Bangladesh is also facing threats from increasing sea level rise. And now this increase in rice production has led to cultivation during the dry season to keep up with the demands, where groundwater is increasingly being used to supply this intense irrigation activity. And this depletion is observed by NASA's GRACE satellite. And by working with the local experts in the region, we were able to confirm these decrease in groundwater through ground-based data sets. So there's a complicated case, right? There's all kinds of impacts that are basically being uncovered with this remote sensing analysis. And we are right now building on this initial synthesis with model simulations and so on. And this is sort of emblematic of many, the water issues that faces many river basins and deltas around the world. So I should also point out that when working on the synthesis, we encountered that there are major water quality issues facing Bangladesh, from contamination from agricultural, industrial, and municipal waste, which we are not tackling here. But it's a good segue to the next task that we are focused on, where within EIS, we are establishing an environment that simulates spatially distributed and temporally continuous estimates of water quality. So this is just a quick movie over the Mississippi River Basin, and now that's being extended to the entire continental United States. So to our knowledge, this is one of the first instances of such a system that can provide both a routine sort of monitoring capability. And the initial focus is to look at nitrate, sediment, and stream temperature over the Mississippi River Basin. And we've been doing the analysis over the entire satellite record to see how the water quality changes have occurred, and are they increasing with more extremes, and so on. Moving on to the next task, which is where we are looking on the long-term changes in the water cycle through a multi-sensor, multivariate analysis in the last couple of decades. So overall, the analysis is increasing that water shortages is decreasing globally, and that's observed mainly by GRACE. And along with it, the planet is also greening. So that sort of represents the increase in agricultural activity. So these two somewhat conflicting patterns impact ET and runoff trends globally, and we observed a neutral ET trend. So there's been a lot of talk about water cycle intensification, but not a lot of studies, to our knowledge, that actually provide a formal quantification. So here is an example of what we produced. We looked at the terrestrial water storage and the intensification. This is a metric. I'm not going to get into the details here, but that basically shows the difference between a later part of the record and an earlier part of the record to sort of quantify the intensification part. So wherever you see warm colors, that indicates that the water cycle is intensifying, and it shows the level of intensification. And so when you run the model without any remote sensing data set, it shows generally an intensification trend. But when you include the remote sensing data set, it shows that those patterns are intensify, or they're much stronger. So in other words, there are these sort of non-stationarities is basically uncovered by this remote sensing analysis. And we also been looking at attributions of why this is happening, and our analysis shows that the anthropogenic factors are the significant contributors to this intensification pattern. And we similar quantifications on other variables also that'll be forthcoming. So now we also looked at the extremes. This is an interesting analysis that where we quantified the vulnerability of major water storage terms around extreme. So again, without not getting into the metric, so generally here the warm colors indicates that the vulnerability is increasing, and the cool colors indicate that the vulnerability is decreasing. So from our analysis, it shows that around extremes, around events like droughts, the vulnerability of surface soil moisture is generally decreasing, because you see generally blue colors, but that comes at the expense of groundwater. In other words, the groundwater, we see more vulnerability around extremes. So typically what would happen is around a drought sort of scenario, you would pump water out of the ground and then replenish your surface soil moisture deficit. So in other words, you don't really see the impact of vulnerability to your surface soil moisture around droughts, but that's because it comes at the expense of groundwater. So another example of now taking this to the future projections, taking what we have learned using the satellite record. So we've been looking at the snow changes in the Rocky Mountains. This is just a quick example where we have run the hydrological models with a couple of different SSP scenarios, which shows warming over the Rocky Mountains, and correspondingly there is a significant decrease in the projected snow changes over those areas. Again, we have been working with the Fish and Wildlife Service in the US to which they have been making habitat assessments for species in the Rocky Mountains based on some of these projections. So finally, switching gears a little bit, like I said at the beginning, we have been thinking about how to enhance the reach of our science beyond the scientists and people know how to work with the data. So you can think of a scenario where anybody out there in the world, a farmer or a student or a manager who could think about questions that may be relevant to freshwater or hydrological cycle. So we've started designing an interface where a person, anybody out there could come and pose a question which hopefully hydrologically relevant. And then we use a series of AI-based tools to provide a meaningful answer to that question. So this is still early, but I'm show you an example of this. So the way it works is it has a series of machine learning tools. The first set of tools take the question posed by a user and then try to reveal the intent of that question. And then once we know the intent of the question, we answer that with a series of machine learning emulators, which are quick to run and they provide a quick answer. So here's an example from it. So you could, let's say somebody could come and ask a question such as, do I need to irrigate my land in some place, Lincoln, Nebraska in the US? So then the system sort of interprets that question to mean, well, this person is asking about moisture availability or perhaps drought. And so it translates the intent first, and then it first translates the intent to be about soil moisture, and then runs the emulators in our background to say, well, the soil moisture anomaly is expected to be negative, and therefore we expect drought conditions and that sort of thing. So it's still very preliminary. So we hope to kind of build on this prototype and make it more powerful. And I also want to point out that NASA has a new system called MAP, M-A-A-P, which has a bunch of neat tools. It's accessible to anybody in the world. So you may have accessed the Earth data websites in the past. So as long as you have one of those logins, you should be able to access all these data sets and able to download them. And this MAP website also has the ability to provide sort of cloud-based analytics. So you could take some of these analysis that we have been doing, and it'll all be available open source. You can build on it. You can create your own account and play with it and do a new analysis and so on. So this is still, again, early in development. So it'll be, more capabilities will be coming, but we've started populating some of these data sets and outputs that I showed today on this website. And I think to wrap up here, so this is sort of our test bed for demonstrating the power of broader data synthesis by wrapping our arms around all the data sets simultaneously, because to really tackle real life examples, you need to have the information about multiple variables, multiple processes, and all put together. And we've also really appreciated this co-development aspect by working with local scientists and stakeholders while we are studying the problem rather than after the fact. And hopefully that will lead to enhancing the breadth of modeling and the reach of NASA science, which is our goal. So I'll stop there.
Thank you, Sujay, and for quite informative presentation. I see there are some questions on already posted on the chat, and I think there are questions that only you, Sujay, can answer. So I'll
So I'm not seeing anything in the chat window for some reason.
so on the chat on Pathable, not on Zoom.
So, oh, I see. Okay,
right,
I'll check that.
Right. So so maybe if you can just glance at those and just offer some verbal responses, or we can always, if you prefer, we can actually just you can actually reply to those on the chat, and we can move ahead to the next presentation in the meantime. Is that okay?
Yeah, I'll start to answer those questions.
Okay, great. So before we move to the next presentation, I just wanted to highlight first that yes, we're doing the Q&A through the questions and answers we're doing through the chat feature on Pathable, and Sujay is already working on responding the questions that have been posed. There's quite a number of questions there. Also on the Pathable platform, you will find the presentation files, and you probably figured this out already, but if you want to get them, download them, they're available for you there. If you have any other questions, just post them in the chat, and we'll get them answered. So let's move on to our next portion with Ivan Lalovic from Jibe, who is going to be talking to us about remote sensing of water quality, which coincidentally, water quality is one of the questions that came up in the chat during Sujay's talk. So these are how these talks and how these presentations connect. So Ivan, welcome, and the floor is yours.
Thank you, Fernando, and thank you, Sujay, and thanks everyone for attending as well. It's my pleasure to be here. So my name is Ivan Lalovic. I am the founder and CEO at Jibe, and Jibe is an early stage climate resilience technology company focused on producing water quality concentration maps. I'll explain what that means. So different attributes of water quality, and then providing that to specific customer segments. And I'll talk about some of the use cases as well as some of our early tractions in the problem that we're trying to solve, as well as some examples of work that we've done with the Nature Conservancy in particular, as well as the IDB. But really important to point out that as an early stage company, early adopters and engagements with early partners is critical in order to be able to derive value and to deliver products that are compelling. So really encourage you at the end to engage, and excited to explore potential partnerships. So fundamentally, the problem that we're trying to address is that collecting water quality or water information in general is very difficult. It relies on sample collections or deployment of instruments that are extremely manual, as well as expensive and time consuming. And the indicators that you get from those measurements are often lagging. They're basically data points that all need to be analyzed and reconciled. So that work, at least for the customers that we engage with, is typically very manual, often in spreadsheets, and there's this very significant lift to interpret these relatively sparse data collections. So most of the operational expense in obtaining this information is supplied to the actual acquisition of data, and much less effort is spent on really the hard data science of interpreting those measurements. So that's really fundamentally the area we're trying to address. And our product is fully autonomous. So the data is delivered to customers in a set of dashboard and analytics views. And so what you see is what's happening right now. So the data is in near real time, and it's immediately contextualized. So because we're using remote sensing, as I'll describe, we have a historical both baseline and kind of variability understanding, so we can put the current observations into that modality or into that view. We enable early warnings because you're not depending on these lagging indicators or sending folks out to the field. So you can plan what the work is ahead. We also provide predictions based on machine learning models, which enhance the ability to plan ahead. And then overall, there are no more blind spots, or there are less areas where you don't have access to data, either in space or time. And it also allows communicating information more seamlessly to other stakeholders. Watersheds are inherently mixed in use, and a large part of the effort that our customers have is to communicate that data externally to other organizations, as well as for regulatory purposes. So having the ability to know what's going on across the entire watershed is extremely valuable. I'll just spend a few minutes on how the technology works. Basically, it's built on the kind of work that Sujay talked about from NASA and colleagues at the European Space Agency that have built science around determining what is the light matter interaction in water, and based on those color measurements, obtaining the concentrations of constituents in water. So what we combine is remote sensing data at the sensor level in space. We use weather data, both current observations as well as projections, and we've developed a proprietary sensor network, which is what's called hyperspectral, which allows us to get more of that optical interaction between the substances in water and light. And so we combine these data sources to basically using physics and a little bit of, or increasingly machine learning, to derive concentration maps of a range of constituents in water. So that's kind of this middle panel of data products. And then the most important part is the kind of interpretation layer, which is delivered through a software application that provides the decision-making tools for end customers. So obviously, given the complexity of water challenges and both the demand side of water, which is insatiable, as well as the climate variability, which is driving additional pressures in the water space, almost all spheres of economic activity are impacted by water challenges and water quality challenges. And we're really focused on the customers that have the most urgent issues. So we're working with drinking water utilities, restoration organizations, such as the Nature Conservancy, the World Wildlife Fund, as well as some of the infrastructure investment banks, like the World Bank and IDB, as well as consumer packaged goods brands, state and federal governments, hydropower and aquaculture. So really across the most urgent needs for translating the value of water into really the most productive economic spheres. Just a brief snapshot of our reach in the watersheds that we work on. Obviously, quite a bit of concentrations in North America. If you don't see a watershed that's really near and dear to you, yeah, please reach out. We're expanding very rapidly and are excited to broadly cover a host of watershed issues across the globe. So this is just a subset of, or a snapshot of where we are today. I'll shift gears for a bit and talk about some of the applications, in particular the work with the Nature Conservancy and the IDB water funds, where we're really trying to enable conservation teams in the NGOs, as well as their collaborators in government agencies and the private sector, to measure impacts of land use change and restoration on water quality. So I'll give kind of 2 or 3 examples of the work that we've done. For the water funds with the Nature Conservancy, we worked in 4 different reservoirs. Obviously, we're scalable because of the access to remote sensing data through, in this particular case, the European Space Agency Sentinel-2 constellation. So we worked in Colombia, Brazil, as well as Kenya. And really the idea was to try to showcase how water quality information can be seamlessly analyzed, processed, and used by conservation teams to understand the effectiveness of their work. So one example of that is looking at basically identifying hotspots, or identifying where there are locations in particular watersheds where either the variability is significant or there are linear trends that are observable. So we can produce a trend map. So on the example on the right is a spatial trend of suspended matter, so suspended sediment concentration. And what you can see are blue areas which are consistently downtrending suspended matter concentration. So there's less sediment that is coming into these areas. So linking where these cold or hot spots are and anomalies allows to understand what are some of the land processes that are driving these trends and correlating it with this period of time. Looking still at this reservoir in Colombia, the Rio Grande Reservoir, this was one of the great examples where eutrophication is actually reversing. So there's a net decrease in eutrophication since 2016. And it's both evident in the suspended matter linear trends. So these are seasonally adjusted long-term trends since 2016, as well as a decrease in overall chlorophyll over the same time frame. Most of the examples that we looked at have a behavior which is reversed, where eutrophication is increasingly driven both by climate pressures as well as population pressures. On the next slide, I just want to summarize some of the work that we've done with the Inter-American Development Bank to look at the impacts of socioeconomic changes due to regional lockdowns associated or following the COVID-19 pandemic. And we've been able to detect water quality changes in watersheds that seem to coincide with the onset of COVID-19 restrictions for several of the pilot locations, most predominantly for the urban areas such as the Guanabara Bay near Buenos Aires or Rio de Janeiro and the watershed and the estuary there, really concentrated near urban outfalls. So very much within cities or very near some of the work, some of the cities' urban water and sanitation challenges. We've observed minimal changes in suburban and rural areas, in particular Lake Ypacaraí in Paraguay, and larger watersheds like the Lake Titicaca that are further away from population centers. And really what we found in this work in the 4 evaluation sites, a significant level of increasing eutrophication, which is driving some of the water quality challenges. And would love to extend that discussion following Fernando's presentation later in this session. A couple of more just highlights of what can be done with remote sensing. So this is some new insight that we can generate along rivers. Basically, we can provide snapshots that project a water quality transect across the entire river length. Here we're showing turbidity in North Carolina for a river called the Cape Fear River. And what you can see is obviously some structure in the turbidity that's related to reflectance from land structures like bridges, roads, dams. But you can see the underlying turbidity for specific dates getting lower and lower as you get closer to the coastal area. You can also identify certain features like a significant chlorophyll uptick that seems to be coincident with a location of a pulp and paper processor. There's some wastewater holding ponds that are in very close proximity to the river at that location. So you can see these kind of effects really without requiring, sending folks to the field to be able to collect spot location measurements. And it provides you a picture view of the entire dynamic of that river as a snapshot and point in time. I also want to talk about some work that's more driven towards machine learning. So this is the process of building a machine learning model to predict nutrients or nitrates in particular. One of the reasons why it is difficult to physically measure nitrates is because the interactions are typically in the ultraviolet. And so there's very limited or almost no signal that's available to remote sensing platforms like satellite imagers. But what we've been able to do is build relationships between the pigments that are visible in the lower Mississippi Basin to nitrate measurements from USGS stations in the region. And what we see is that we have the ability to build models that are of extreme acuity, so be able to measure and distinguish very low concentrations of nitrates very accurately. And what that enables us to do is then build nitrate maps based on similar models, again, based on remote sensing observations, not directly of nitrates, but of the constituent pigments that are trained through this model building exercise. So this is very exciting because it enables mapping of nitrates across the entire basin in real time from a range of both publicly available satellite imagers, like from NASA or the European Space Agency, or commercially available satellites. And with that, I would encourage you to get started. It's very easy. What we provide is an access to continuous monitoring through the software platform. It's really a low risk software subscription, so it's very straightforward to get scaled coverage. So start with a small area and then scale the coverage over time. It's complementary to current monitoring efforts. And in addition to increasing the area coverage, we can add real-time data access through the sensor deployments, APIs that enable specific data to be extracted directly through the platform, and more and more predictions. So contact us with any monitoring needs, and really excited to build a platform that fundamentally enables collaboration and collective action at the watershed scale. So we really view ourselves as an information platform that facilitates sharing of water quality contextualized data with others in the watershed. And email is listed here, and really happy to address any questions through chat on Pathable.
Thank you, Ivan. Thanks. Very exciting, very innovative techniques and results. Yes, there's probably at least one question for you on the chat, so I will let you respond to that, and we'll move to the next presentation, which I will give. And since that work also, Ivan, involves you, if there's any questions that pop up while I talk, feel free to jump in, and we can certainly also try to address those after I'm done. So let's move everyone to our next presentation. So I'm going to share my screen, and hopefully it'll work. So you should be seeing my title slide, and Ivan briefly referred to this exercise that we did with COVID-19 in Latin America, and I want to take a little bit of a deeper dive, because it ended up being a very interesting project with some very, very interesting findings. And so the question was, did COVID-19 produce impacts on water quality in Latin America water bodies, right? So that was the sort of the question coming in. And when the COVID-19 onset happened, we started to see documented effects. Some of those certainly led by NASA, in terms of, for example, improvements or at least temporary improvements in air quality, in atmospheric quality, because of the lockdowns, right? So we asked ourselves a question, what about water quality? Is there a signal of lockdowns due to COVID-19 that could be perceived in water bodies? And this work was sponsored by the Inter-American Development Bank, with participation of a lot of their staff. I acknowledge the team below. From Jai, Ivan Lalovic, and Sarah and Philip, as well as Adam from the IDB, Jihoon and Raul, and myself from Nature Conservancy. So the underlying question was whether COVID-19 had indeed caused any impacts. And so one of the things that we wanted to do is first try to develop like a rapid assessment of this, because you know, if you go back 2 years ago or a little bit more, actually, when COVID started, we just didn't know how long it was going to last, and so we wanted to try to take advantage of the opportunity that some data was becoming available to make an assessment. So the first objective was to make an assessment of water quality changes during that lockdown period, the sort of before and after type conditions, right? Before the lockdown, after the lockdown, and see if we picked up any signals in water quality. Second was to actually use remote sensing to do some data gathering. You know, get because these data sets, as Ivan was presenting, and certainly Sujay as well, these data themselves, not just the analysis, but the data themselves, can be useful products and useful information for a whole host of applications. So we wanted to make sure that we did that. And third, because of the work of the Inter-American Development Bank in working with governments and countries, with governmental agencies, with water utilities that may not typically use remote sensing, or at least not operationally. You know, they may use remote sensing for some information gathering, but not data of remote sensing or remote sensing data used operationally. Was something that the IDB wanted to introduce through this project, right? So I think those were the three sort of big objectives going into this. So primarily the scope of the work that was done was, you know, focus on, you know, acquisition of satellite data. And as Ivan explained, I won't go through the methods themselves. I think Ivan covered them very well, but it's primarily a combination of Sentinel-2 and Landsat 8 data from the European Space Agency and NASA, you know, primarily. So acquire the data, you know, translate that data, that's primarily reflectance values, to water quality calculations, and focusing on primarily chlorophyll, which is, you know, a surrogate measure for nutrients and photosynthetic activity, and then sediments and turbidity, which it's a more of a measure of you know, transport of sediments into water bodies, right? So we're looking primarily at nutrient type activity in terms of water quality, nutrient type activity, and sediment type activity, right? At this point. And see if we could pick up a signal on any of these, or maybe on both of them. Process the data and generate, you know, generate water quality time series and maps, right? Which is what are typically used to evaluate, to assess, to support decision making. Do this entirely through satellite data was the objective, pre and post lockdowns in COVID-19. So that's a little bit of the scope. And just a little bit in terms of the data itself, and Ivan mentioned some of this already, but I did want to reiterate, you know, some aspects that I think are very valuable from the practitioner standpoint. This data is pretty high resolution, so it's in the vicinity of 10 to 20 meters, and it actually this actually provides a quite a different picture, and we'll see some results. I typically describe this to students in my classes. This is like, you know, watching television in the 1970s versus watching television today, right? The level of resolution that you get, you know, if you look at how we traditionally collect water quality samples in a water body, a reservoir, a river, you know, these gauges tend to be, you know, spaced, you know, sometimes kilometers, right? Now we're going from kilometers to tens of meters. You know, we're looking at orders of magnitude. That's about the level of resolution that, you know, television sets have improved over the last few decades, right? And again, the focus is on chlorophyll and on turbidity in the water column and suspended matter in terms of trying to measure sediments. Ivan introduced the concept of virtual gauges, and virtual gauges are useful for very practical purposes, because traditionally the way we collect water quality data is we place a gauge, right, in a given location, and then monitor water quality location in that gauge over time, right? So if you're able to do the same exercise, but now it's a virtual gauge, so you're focusing your satellite imagery on that location, and then monitoring that over time, you sort of get a little bit of an equivalent take on the measurement of water quality. Also, the virtual gauges allow you to focus on areas of interest. For example, downstream of relevant discharges that could be polluting to the water body. So you can actually focus your attention on that, even though you're covering the entire water body with a resolution of 10 to 20 meters, right, which is remarkable in itself. You can also do the more traditional exercise of focusing on a particular location and then monitoring that over time. So that's something that we implemented here. For the purposes of the study, we try to focus on 4 major water bodies that sort of capture different conditions. Guanabara Bay in Rio de Janeiro, it's a bay downstream of a heavily urbanized area, right? With lots of water quality issues. Guanabara Bay has been subject of studies and improvements in water quality efforts for decades now. So that's one of the water bodies we focused on. The second was just going vertical to another relatively urbanized area, a river basin near Buenos Aires, Argentina, the Rio Reconquista Basin. Again, heavily urbanized, lots of activity. Wanted to look at impacts and on that basin. Then Ipacaraí Lake in Paraguay. This is a lake that it probably has less urban type activity. It's got some economic activity. It's a recreational area. It is also used as a water supply reservoir. So keeping good quality in the reservoir, it becomes important. And then Lake Titicaca in Bolivia and Peru. Again, focus on water supply, also located in the fringes and in some relevant populated areas. So we looked at lakes, reservoirs, river basins, and try to capture a combination of geographical locations as well as different types of situations. So I want to give you a little bit of a rundown of the sort of answering the question, did COVID-19 affect the water quality in these 4 water bodies pre and post COVID-19 lockdowns? That's a little bit of the big question. So let's move on. So the first thing I'll say here is that because you're monitoring the entire lake continuously, you can actually start looking at things in ways that, at least for me as a practitioner, are very interesting to see. And what we have here in this slide, this is Lake Titicaca, a map of Lake Titicaca, right? If you've ever taken a class in limnology or lake water quality, the first thing that one of the first things you're taught is this annual cycle, right, of the lake, of circulation, right? So during the colder months of the year, the colder season, a lake tends to the water on top of the lake tends to cool because of the colder environment. When it gets cooled, it gets heavier and it promotes circulation. So in the colder season, you see a well-mixed lake. And if you look at and let's start here, if you look at the months of June, July, and August, which is this time of the year, but in the southern hemisphere, this is the cold season, you actually see that well-mixed, where the majority of the lake is a very similar concentration. These are concentrations of suspended matter, but you can actually look at this in chlorophyll and turbidity and see about the same thing. You see this in the colder months, and you also see them in the months leading to that, right? So if you look at May, March, April, May, you start looking at better mixed conditions. In the warmer months, so December, January, February, and in the months leading into that, September, October, November, in the warmer months, what you see is the stratification of a lake, right? Because so the top of the lake gets warmer. If it gets warmer, it gets lighter, and it tends to stay on top. And then you see this stratification, and then you start seeing conditions that are different across the lake. So what you see here is that actually that cycle, that annual cycle, but you see it at very high resolution. If you ever looked at maps of water quality in a lake, you may be able to see maps like this, but they were generated with much more sparse data that was a lot more distributed spatially. Now you're looking at these maps being generated at spatial resolutions of 10 meters. So this is in itself, without speaking of COVID-19 or anything like that, this in itself it's an important practical advance in the field of monitoring water quality, right? I also like this, the reason I post the seasonal cycle is because, when you're looking at lakes and reservoirs, that's one of the first things that, as in limnology and lake water quality, is one of the first things you look at. Now let's take a look at the lockdown data. So the complementary part to this is to go out to each location and figure out when the lockdowns occurred. So through our colleagues at IDB and working in partnership with the governmental agencies, we were able to obtain, the lockdown periods. A lot of these lockdowns, as you know, occurred starting in March 2020, and what probably was different in each location was the length of the lockdown and whether additional lockdowns were introduced along the way, right? So these were the lockdowns, the dates, and we focus on 2020 and 2021 for this analysis for the most part. By the end of 2021, things were a little bit going back to normal, and water quality patterns sort of shifted back to more stable, form. So this is Buenos Aires and Paraguay for the Rio Reconquista and for Lake Ipacaraí. And these were the lockdowns for in La Paz in Bolivia, La Paz El Alto, for Lake Titicaca, and in Rio de Janeiro for the Guanabara Bay, right? So we saw, for example, in Rio de Janeiro, there was very few lockdowns compared to other locations. So that has an impact in what you see. So let me show you some of the results, and this is Guanabara Bay, and these are differences. So we took differences pre-lockdown versus post-lockdown, right? And the lighter colors means negative differences, which means that there was improvement in water quality. There was less pollution. In the redder areas means there's more pollution. So here, the first thing you'll see, and this is chlorophyll, right? This is chlorophyll, Guanabara Bay, pre versus post lockdown. The majority of the bay is either at yellow or at blue-green. Blue-green means really big difference in terms of improvements in water quality. There's definitely a signal in chlorophyll A against chlorophyll A, meaning measuring more of a nutrient type of pollution. Definitely a signal, lots of less pollution pre and post lockdown in Guanabara Bay. You can look at Guanabara Bay now in sediments, and the difference is not as pronounced as in chlorophyll, but you still see the majority of the map being mostly yellow, which means, milder but improved water quality. So in Guanabara Bay, there was definitely a measurable impact of improvements in water quality pre and post lockdowns. This is Lake Ipacaraí, and these are some of the virtual gauges that were monitored. These are all virtual, and you can actually see the time history in some of these. You can historically, going back 5 years, you can take a look at what was happening, and depending on the location along the lake, you see a different water quality pattern, right? But you do see, for example, in one of the virtual gauges, you actually see a spike in water quality. In the others, you sort of seasonal cycle with some interannual variability. But we focus on the pre versus post lockdown period in the lake. And then here you see these are the maps for the lake. Left panel is chlorophyll, right panel is suspended matter. Again, in this case, the darker colors correspond to improvements. The bluer colors correspond to decreases in water quality, or to water quality that's worse. For the most part, we see that throughout the annual cycle, the lake undergoes improvements in water quality. There are some blues, though, right? Both in chlorophyll and also in suspended matter. And look at particularly these months of September, October, November in terms of, so there is something here that needs to be investigated further. We're just looking at the data, but our working hypothesis, is that it looks like there was some limited human activity during the initial lockdown. So and Ipacaraí had really, if you look at the lockdown schedule, lockdowns in 2020 were for a long time, right? And then they started being released easily in towards the end of 2020 and beginning of 2021. So there was a lot of limited human activity, and that explains a lot of the red in these places. But then, as restrictions eased, there was a lot of increased travel to the region. This is a fairly touristic type location, and then that could have caused then the conditions to the worst water quality to emerge again. Okay, so it's not a definite conclusion, but that's what we suspect in terms of the timing and in terms of what we're seeing in the data. This is the Rio Reconquista Basin. So this one is interesting because in addition to looking at the river itself, we looked at the tributaries that lead to the river, and you can actually each of these virtual gauge locations tells a different story because they're located in different places within a basin that it's pretty highly urbanized, so the remote sensing itself actually produces results that are interesting, even even non-COVID, under non-COVID conditions. But when you look at one of these locations, and we looked at all of them, but when we look at one of these locations, again, you see that pattern, right? We see a pattern of things improving, water quality improving significantly, during in this case, this is suspended matter in one of the locations in the Rio Reconquista. And you can actually see here that, the lockdown schedule in the Reconquista Basin, was severe at the beginning. Then it was pretty much social distancing, but normal activities. Then another period of confinement in 2021. So you actually see, like, on and off. So what we're seeing here towards this blue here, it's probably likely coincides with easing of the conditions and things going bouncing back to poorer water quality. And then Lake Titicaca, we saw lesser impacts, and again, this is a lake fairly large. You do see some reds, so some improvements in water quality in this case. In locations that typically are close to urban areas. So when points of the lake were close to urban areas and there was lockdowns, we did see a little bit of an improvement in water quality. But the lake, it's fairly pristine and has fairly good water quality. So the impacts there were not. The impacts of COVID-19 were not as pronounced. Again, with the exceptions of places close to, for example, La Paz. La Paz is about here, close to this end of the lake, and you can see a little bit of improvements there, but it's not as pronounced. So this is just a summary of the key results. We were able to pick up signals of improvements in water quality pre and post lockdowns using remote sensing in some of the locations. I think probably with the even in Lake Titicaca, you know, closer to the areas, we're able to pick it up. So it was measurable. It is measurable at high resolution. And the impacts on each of these locations are, you know, we've discussed them already, but I'll leave them in my slides. But to me, the more is so what does this mean for the future, right? So I think it helps. You know, remote sensing can help in to try to optimize where we sample. You know, because remote sensing is not going to replace completely ground gauges, but it can help you decide where to sample in more detail, right? Because even the 10 meter pixel, that's still probably in some places is going to be too large, right, to get some good resolution. Where to plan or develop remediation or investment efforts in terms of improving water qualities? Where do you build treatment plans? Or where you implement nature-based solutions for improvements in water quality? Those locations can be scouted or can be screened using remote sensing data. And certainly, you know, it helps understand the ecological impacts, you know, post of construction, infrastructure projects, or other disruptive events, you know, like COVID-19. So that's what I had. I hope this was enlightening and that you found this useful. And thank you very much. I will stop sharing my screen. And since I've been speaking, I have not been able to respond to questions. I don't know if Ivan, but we still have a few minutes where we can respond some questions. We can answer some questions. Like I said, all the presentation files are there. The one comment that I wanted to make that I think it's relevant is that both the study that Ivan presented on water quality in water funds and this study on COVID-19 are in process of publication. They actually have been accepted by the journal, and we're waiting their press, so they should be produced soon. So this the entire details of this work will be available very soon. So let me see if I can scout some questions here. Ivan, have you been able to answer your questions?
I think so. Yeah, I've been responding in individual questions as a reply. So there's a little button there.
Okay.
Well, great questions. Yeah, on a range of topics. Mostly seems like precision and accuracy, and some of the challenges that remote sensing has there, and how it compares to the SON deployments or in situ measurements.
Okay. Well, I think that sort of gets us to the end of our session. If there's any other questions that can come up, feel free to post them in the chat. Otherwise, I know you have other sessions probably to attend. So it's been a pleasure, being here with you today. I hope you enjoyed the session, and I hope this was informational. Again, files are there for downloading, and these results on the remote sensing and water quality will be published very soon. Well, wonderful. I think we can close the session, everyone. So have a great rest of your day, and I'll probably see you in another session very soon.
Thanks, Fernando.
Thank you,
Sujay. Thank you, Ivan. Thank you. Thanks, everyone.
Thank you.